How about you focus? Oh my goodness, why aren't you focusing? I don't know if it just doesn't like this computer, because it doesn't seem to have this problem when I use my computer. Certain distance that you want to be from? Okay, fine. Okie dokie, let's get started. So, if you guys remember last week, we started the CMMR, and I said I'm not going to explain how the machine works until the next week because you don't need it for what we're doing today. You really only need to understand it for the excellent stuff. And on top of that, keep in mind that I'm never going to ask you on the assessment how any of our machines work. The only reason why I explain how these machines work is because I think it helps you understand what the data is trying to tell you. So do keep that in mind. So the first thing we have to think about with CMMR is that CMMR is going to be using magnets in order to collect this data. So I'll write down CMMR. So some hints to kind of get you guys thinking about what this does. Oh my goodness, come on. What is with this camera? It used to work all the time. I think it's not liking this computer. Are you just not going to focus ever? Where does your new docking camera? There we go. All right. So the NMR is referring to magnets. And what do you think the C is referring to? Carbon. Yeah. All right. So the thing to remember with our atoms is that when we have various atoms, they do have a spin to them. So the nucleus will be spinning around. This happens with odd number atoms. So atoms with an odd number, I should say odd atomic mass. Let's be better about that. Have a nuclear spin. And this spin is random. So that's what we see down here with this little image there. Spin is random. Now, when we think about carbon and its atomic mass, what's its atomic mass number? 12. So that's an even number, isn't it? So in theory, when we think about this, it's not supposed to work. And so we have to specifically use carbon 13 for this. So you might see it as being 13 CMMR, and it's using the isotope of carbon 13 for this to work. You don't have to worry about explaining that. I'm just letting you know how, even though carbon is an even number, how we can still get it to work. Are we okay with that so far? Like I said, you never, ever, ever have to explain how the machine works. Now, what I can do with my atoms is I can start applying a magnetic field. And when I apply a magnetic field, I can get my nuclei to spin in the same direction. So that's the other thing that we have to keep in mind. The spin will align. Yeah. So it's like when you know how you have a compass and you can make it move around with a magnet nearby. Otherwise, it'll just align with the Earth's magnetic field. It's kind of like a similar thing. These guys will spin around randomly, and when I apply a magnetic field, I can get them all going in the same direction. So when I have a magnetic field, I can force my atoms, that nuclei, to spin in the same direction. They align. And you have a couple of images there to help you kind of visualize what I'm talking about. So in this case, these are my atoms without the magnetic field, and they're randomly spinning around. And then what I can do is I can put my atoms in a magnetic field, and then they're going to start to align. Most of them are pointing upwards. So this guy, and this guy is going up that direction. These two are going in the other direction, but they're all in the same plane, going vertical. Are you okay with that so far? All right, keep going. All right, so the next thing that we then think about is this bit of data here. And what this is trying to show you is how much energy is required from that magnet to flip the direction of the spin. So right now the spin is going upwards as a net, and I'm asking myself how much energy and strength from that magnet do I need to put in to force it to flip the other direction. So that's what this is referring to, is how much energy do I need from that magnet in order to cause the alignment to flip. So this is showing how much energy is needed to cause the flip. Hope if I could spell properly. So that's just telling me how much energy do I need. Now, depending on what's attached to that carbon, that's going to vary how much energy you need. I'll just move that up. And so that there is what's going to cause our carbon environments. So if you guys remember that we were talking about last week, if the molecule is symmetrical, we have fewer carbon environments because they have the exact same list of stuff that's attached to it. So when it goes into this machine here, both of those carbons in a symmetrical molecule are going to need the same energy because they have the exact same list. I'll leave that up for a second for you guys to copy that down. And like I said, you'd never have to explain how the machine works. So don't stress if everything that I'm saying sounds like gibberish. But it's good to kind of have an idea. All right, can I keep going? Yes? All right. So I just want to go back to question number 1 that you guys have done in your packet, just because we've been working through this question quite a bit. And I just want to look again at the CMMR data here. So we know that there's 3 different peaks here. And if we look at the bottom, the ppm, that is referring to the strength of the magnet. So with these 3 different peaks that we're getting, what we're trying to show is each one of those carbon environments, how much magnetic energy do I need to cause that flip? So that's what we're looking at here. Since this molecule was symmetrical, we had fewer carbon environments. And that's because if you guys remember from our last lesson, they have the exact same list of stuff attached to it. All right, we okay so far? All right, next page. Okay, so what we can actually do with this information, I'll come back up to this in a second, is that the CMMR data can be used to identify function groups as well. So you can see here on this table, I've given you a visual representation of all the different function groups and roughly where they would be on the CMMR data. You guys also would have, if I can find the sheet that I just pulled out, which is not here, so I put it over here, on your resource sheet as well. What you'll notice is that on the back page, I have the approximate values for this chemical shifts for the CMMR data, and it has a list with all the function groups stating roughly where that functional group should be. Now, some things to note about this is that this is less accurate than the IR data. So use the IR data first to figure out what function group there is and use this as a confirmation. If it's not exactly perfect, don't stress too much about it. The IR is the one you should be trusting. So, like I said, this is just a visual representation of the same stuff that's on the sheet. The reason why I want to take this visual representation is I wanted to explain why certain things are in certain locations. So the reason for that has to do with the electron negativity. I believe, did we talk about it last year? Because we were talking about polar and nonpolar molecules, weren't we? Yeah. So some things to keep in mind when we come to electronegativity is that the smaller the atom is, the more electron negative it is, and the closer it is to group 17, the more electron negative it is as well. The most electron negative atom in our periodic table is fluorine, so that's the one that's going to have the strongest attraction to electrons. So just be mindful when we're talking about electronegativity, we're talking about the atom's attraction to shared electrons. So our covalent electrons. Are we good so far? Yes, no? Okay. So that's what we're thinking about trend-wise. Now, what happens with the CMMR is that if the carbon is attached to something electron negative, it's going to pull those electrons further away from the carbon, exposing its nucleus. So let's say, for example, I have this carbon that's double bonded to the carbonyl. So this carbon that is a carbonyl. So it's attached to an oxygen. So I'd have C double bond O for my example. Now, if I wanted to show these guys as electrons, I could actually show them as C 1, 2, 3, 4 electrons. This is a little flashback to Lewis structures, I think. Yeah? Now, when we're looking at our periodic table, oxygen's more electron negative than carbon. So oxygen's going to be pulling the electrons closer to it. So what I would then see is my carbon atom, and then these electrons in theory would look closer, like visually, to that oxygen. And what that does is that it leaves the carbon nucleus exposed. Right, keep going. Okay so far? All right, so when we have our carbon nucleus exposed, it's going to require more energy in order to flip it. So what we refer to things down here as, we call these guys de-shielded. De-shielded means that they're no longer shielded by the electrons. So if they are de-shielded, they will be what we also would call downfield, and they would have more energy to flip. Whereas the stuff that's over here tends to be more shielded. So we tend to see more of other functional groups over here, or like just the carbon with the hydrogens. Again, never need to explain this. It's just so you understand why certain functional groups are in certain areas. Worst case scenario, you don't understand it, but you can look at the resource sheet and just look for your functional groups. I don't remember, it was on the last page. Yeah, I'll go show you the last page. Yes, I should. All right, change it. Ready? So I just want to show you guys this in real life. So I've given you two organic molecules, pentane 1-ol and pentane 2-ol. Both of these are going to be structural isomers of each other because they have the same carbon number and functional group. I'm going to draw it out so you guys can see what they look like, just to help visualize. So pentane 1-ol, CH3, CH2, 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 OH is what we got over here. And then pentane 2-ol is the same structure, but with the OH on carbon number 2. I'm going to zoom out so you guys can see both of them at once. Now, what you'll notice with the CMMR data is that both of these guys have 6 carbon environments. 1, 2, 3, 4, 5. Sorry, 5 environments. 1, 2, 3, 4, 5. And then if we look at this one down here, 1, 2, 3, 4, 5. So 5 as well. And I'm just going to write EC or CE to shorthand it. But do these two spectra look the same? No. What we can notice here is that these guys are quite clustered together, and you have one that's coming a little bit further out. And this one here, we have 2 that are a bit further out and 3 that are clustered together. Yeah? So first thing that we can note is that this guy over here that's pulled out quite a bit. That one, when we look at the CMMR information, and I look for stuff that's carbon attached to an OH, which is the alcohol, it says that I should see a peak between 50 and 60. So that's where the shift should be. And when I look at this guy, that one is just above 50. So that should be my C attached to my OH. This one is a little bit higher, but it's still within that range of 50 to 90. So that would be my COH. So it helps confirm what I'm looking at. Now, the thing is, since this guy is on carbon number 2 instead of carbon number 1, is that the electronegativity of this oxygen here is going to influence this carbon, who's then going to influence the other carbons as well. So that's why we see that one of them's been pulled a little bit down, and the cluster is only of the 3. In this guy here, at the top, we see that there's a larger cluster, which is showing me that I have my chain. So 1, 2, 3, 4, 1, 2, 3, 4. So that kind of shows like, oh, these are 4 carbons attached to each other. This one here suggests I only have 3 carbons that are probably in a chain together, like that, because this guy broke up the list of 4. So we can use it as a way to kind of help guide us when trying to decide which of the potential isomers we have. Are we okay with that so far? Yeah, hopefully. Seeing how long I've been talking for, I'm mindful I talk a lot. All right, so let me grab that question number 1 again, so that way you guys can see what I'm looking at for the excellence criteria. So for this guy over here, one of the things I need to see if you're aiming for excellence is I want integration of your data, so that way you're showing that one bit of information backs up the other bit of information. So right now, question number 1, if I was to mark it with what I've done so far, I would still be only giving it a merit, because I do have the right answer, but I haven't fully explained, why the 7 carbon was eliminated. I also haven't linked in my spectra together. And the last thing I haven't done is I haven't justified with the fragments. So fragments we'll talk about on Thursday, but I can talk about how we're integrating the information today. So multiple ways you guys can show me that you're integrating and using the spectra together to answer your question. The first thing is to basically just back up your IR data with the CMMR data for functional groups. So right now I see that I said that there was an OH, and then I can go, ooh, does one of my CMMR data pieces match a an OH? And I can see that, again, a carbon attached to an OH, I should expect my CMMR peak to be around 50 to 90. And when I look at this guy, it's almost at 80. So this one here is telling me my CO, and that's going to help confirm the alcohol. So I've written this now in green because that is the excellence requirement. So for the excellence, I need to figure out what it's not. You need to have integration. And the last thing is your fragments. So we've started talking about figuring out what it's not, and today we're doing the integration. So that's something I can use to help justify what it is. All right. Another thing that I can do to show that integration is I can connect my mass spec to my CMMR. So from my mass spec, I know I have 7 carbons, but the CMMR data says there's only 3 carbon environments. So I can link these two together, and I can state that this suggests symmetry. So number of carbons in mass spec and CMMR don't match, so there must be symmetry. Which is what we figured out when we were doing our working anyway on the next page, if you guys remember. So the stuff in green is starting to show that excellence level thinking. Not only have you figured out what the molecule is, but you're telling me how you did it. Questions, concerns, comments? So yeah, CMMR is going to be really important because that's kind of like the middle ground. It's the one that kind of integrates the two together. Or I should say integrates the 3 spectra together, because we can use it to confirm functional group. We can use it to help figure out carbon number and carbon environments. All right, you guys ready for me to move it? You guys, nope, not yet. Okay. Any other questions, or should I just stop the recording now? I know let's do another example later. I want you guys to practice it first. Give a break from me talking.